Last speaker in this session is Valery Smyshlyaev from University College London, and we asked him specifically, as he lives in both the former Soviet camp and the Western European camp, to talk to us about the influence of Joe's ideas on asymptotics and geometrical theory of diffraction to what was going on in the Soviet Union at the time. So over to you, Valery.
Thank you very much, David. Thanks to the organizers. It's a great honor to be here and with this important mission, I would say mission impossible, to try to give an overview, a brief overview of Joe's influence, as I said, as I proposed, behind the Iron Curtain, right? Actually, as David hinted, from my own perspective, this is where I grew up. I grew up on the other side of the curtain, where I did my in this Russian, then Soviet diffraction school, and did there my PhD and early postdoctoral years. And yeah, this is where I personally learned about Joe Keller and his work and things. So then I moved on this side of the curtain. Actually, either yesterday or the day before, I never knew how it was to celebrate 25th anniversary of my arrival. It was 29th of February. Doesn't happen every year. Right. Okay, and then I feeling honored when was charged with this important mission. Oops, what I've done. Yes, this is my talk is, I felt that I should go to fact-finding mission back to St. Petersburg, Russia. Actually, that coincided with myself being in Finland week before last. So I got a train to St. Petersburg and had a chance to see Valery Babbage, my former supervisor, and a couple of other colleagues. So fact-finding mission to St. Petersburg last month, 2 weeks ago. It was, here is Valery Babbage, my supervisor, who I kind of informally interviewed, right? Recollection and some of what I learned and refreshed in my memory I'll try to report here today. So for me, he's one of the kind of leaders over the last several decades, including these days of St. Petersburg Diffraction School, which itself was greatly influenced by many sources from folk school from Russia, but also from Joe Keller's geometric theory of diffraction ideas in particular. So on my fact-finding mission, fact number one, bearing in mind the title of my talk, Influence Behind the Iron Curtain, fact number one was that there was no Iron Curtain. No Iron Curtain in mathematics. A quotation from Valery Babbage, and not in mathematics, even in the 1960s. The Western journals like this famous Courant Institute Communications Pure and Applied Maths journal was easily available. That's in contrast to other sources, New York Times, Washington Post, and other mainstream media were not available. Incidentally, not for record, but they learned also from my colleagues, as often happens in maths, but not only in maths. What people discover more recently was known in Russia and former Soviet Union a long time ago. Even then, these sources were regarded as fake news. that many years ago. However, we didn't have a chance to check for ourselves. They were not available. We were said, believe us, they are. Right. For a Russian Soviet school of diffraction, one of the main founders was Vladimir Fok. Here is his photograph, and he is one of sort of influential figures for that somewhat parallel but not totally orthogonal process back in Russia. So he, in fact, formulated what is kind of conceptually similar to geometric theory of diffraction in a series of his papers starting from 1940s, from 1946, immediately after the Second World War. And again, in fact, iron cut was not necessarily kind of reciprocal thing, right? So not all the Russian papers, not all of them were translated then, but a collection of Fox papers is now well known, and it is has been published in 1965, right, in a book. So it includes all those sources. So he has done quite a few important contributions. So what he sort of formulated as a principle of locality, in some sense, could be seen as conceptually similar to key postulates of GTD in geometric theory of diffraction. So that's what it is. So essentially, specifically for philosophy, is if you want to understand the principle of locality, right? So if you want to understand what happens in a non-geometrical optical situation, take the magnifying glass and look inside and see typical pictures, like in this case, immediate neighborhood of the point of the grazing incidence. Identify appropriate canonical problem, try to solve it, and find the key characteristics to feed it back to the bigger picture. Okay, now, and people know this is what is now recognized universally as Fokler-Antovich problem and Fokler-Antovich method, and this whole solution is a famous Fock integral, right, for local asymptotics for the diffracted field in the immediate neighborhood of the tangency point where the light meets shadow, right? The shadow effect appears in geometrical optics, breaks down, right? So this is all now well known, some kind of canonical problem called Fock's problem, Fock's integral representation of the field in terms of Airy functions. Airy functions are these fundamental objects connecting light and darkness, right? Oscillations on one end and exponential decay on the other, and enter in the form of intricate integral. Okay, now again, it's all quotes from Babbage of week before last. He said that what was recognized even then in late 50s, early 60s, a very important result of Joe Keller of 1956 and 1959, and I fetched here, like in St. Petersburg in the 60s, you can easily fetch those papers. So I did. I had on my talk one publication, 1956, of Joe Keller, diffraction by convex cylinder, and a follow-up paper, Levy-Keller, three-dimensional version, right, of diffraction. So essentially, according to Babbage, very important original contribution is asymptotics of the exponentially small field deep inside the shadow, right? Deep shadow asymptotics, and Joe Keller in these two papers derived this new formula, well-deserved box, as I put it, my box. Right, so essentially exponentially small field, so there is this exponential contains order k minus 1/3, right, these parameters, complexified zeros of Airy function provide exponential decay of order 1/3, and initially Joe was able to arrive at this formula from kind of intuitive arguments, kind of intuition of a genius, you could say it. So again, a quote from Babbage-Boulderiff, very important result describing the field in the shadow behind an obstacle on the basis of heuristic consideration. This formula was first derived by Keller in 56 for the dimensional case, and then in 59. So all the argument is here. So essentially, to if there is a source and there is a receiver, right, you should guess what happens here, and there is some kind of qualitative arguments which Joe was able to translate into concrete formula, and then made people busy trying to sort of to work out how it could be derived in a from possibly other considerations. So locality arguments and deep shadow qualitative arguments on the creeping waves versus shed energy splitting and reciprocity arguments, right, were used for deriving formula relay. It's kind of, it is symmetric with respect to source and receiver. Involves certain kind of canonical diffraction coefficients or whatever you could say in both points of incidence and points of shedding, geometrical spreading on the surface in a three-dimensional case, surface geometrical spreading, so everything is a kind of no competitors to this important result of Joe, even on the other side of the Iron Curtain. Right. Then that particular work has indeed much influence in Russia, former Soviet Union, and the people try to work to confirm it from different arguments. One is based on boundary layer and matched asymptotic techniques and extensions and matching and everything. Some details can be found in book of Babic-Kirpichnikova. Then on both sides there were activities on deriving uniform asymptotics, again much inspired by this Donald Ludwig's in current of the 1960s, and that's all reflected and refined in some way in on the Russian side. And if you were to do rigorous mathematics, this is the problem where you can easily sort of spend all your life and not find it is not enough to prove the error bounds for the exponentially small errors. There was some activity here, and Filipov and others, inspired also by Joe, worked hard to justify the to prove rigorously the errors. Right? Joe just writes formulates correct, right? And others you have to work hard to analyze it. Okay, so for others, kind of talking about the influence, right, behind the curtain, not curtain. So the other Keller's work, which again quotes, significantly influenced Russian diffraction, and that is one with Friedlander, Keller, and then Keller, Karl. This is an attempt to extend geometrical optics to include complex rays. So there were, and one of the papers on the Russian side, Babic-Rusakova, analog of Rayleigh waves in propagating in elastic body along a curved free surface. Uses certain ideas from there, right? Complex canals and surface rays in connection with the theory of skin effects were considered earlier by Keller and Karl, right? It can be found in that publication. So in fact I fetched this paper, as now these days everything is translated, even those publications of 1962. Yes, I fetched appropriate sections here. So the key technique there for this Rayleigh type high frequency waves, right, along curved surface. The key technique was developing complex A canals. There is acknowledgement of 11 Keller color there, and Babic formula this occasion to publicize. Some people argue this is the first occurrence of what has later become famous as the Berry phase. Publication of 1962. Then it was realized this is more fundamental effect, where you develop some generalized version of geometrical optics with a complex aconal, and you arrive. I highlighted it here. The following three factors show that the curvature, blah blah blah, rate of change affect only the phase of the Rayleigh wave. Right. This is what is now known as the Berry phase, appears fundamental. But again, if you go back for occasion of this meeting, this was all much influenced by Joe's development of complex rays theory. Now, John the other are not one of the the first one, J.O.H.N., right? Already mentioned this as one of important contribution. Keller in Rubinow, 1960s, asymptotic solutions of eigenvalue problems, right? This is the first attempt. It's again, intuition of a genius was required, was needed to realize that geometrical optics ideas could be used for characterizing asymptotics of eigenfunctions and eigenvalues, right? But here you have to close things together with so-called quantization conditions, right? Drawing asymptotic formula, yeah, manifolds. So this also influenced much mathematics in Russia, former Soviet Union. In fact, not only in the diffraction community, even wider, and not only applied, but on a quite purish side, right? It appeared to be related to various geometric objects, characteristics of topological or whatever, right? In Maslov index, Maslov-Arnold, and so on. So that was one important original sort of contributions which kick-started a whole bunch of activities in the former Soviet Union, but not only. Okay, now this is the this is the John, right? And first John produced front page, right? Like this. I'm not the first one. Geometric theory of diffraction is a famous paper. Some huge number of citations. Just Googled yesterday out of curiosity, 1962. And I asked, again, apart from St. Petersburg School, there was quite a number of groups much influenced in the former Soviet Union. So Moscow to St. Petersburg, I think it's like Oxford to Cambridge, right? So, and other way around, there's historical rivalries. Nevertheless, I am St. Petersburg guy, right? Nevertheless, you have to acknowledge Moscow's School of Diffraction, one of the prominent representatives of that time, Vladimir Borovikov. So it was he and his colleagues were also much influenced by Joe Keller and his ideas from geometric theory of diffraction. So in fact, Borovikov, a couple of books, one of them is not translated, I believe, but very important, very influential in Russia. So in fact, some people claim this is, again, was much influenced by the GTD ideas, and this is where first Borovikov developed some ideas like treating high-frequency asymptotics in terms of analyzing singularities in the time domain and doing Fourier transform, which is then became base for micro-local analysis, very sophisticated, sometimes too abstract mathematical technique, right? And there is a book which is translated, Borovikov, Kildmer, Geometric Theory of Diffraction. So in attempt to summarize, which is mission impossible, as I said, so there, again, from myself interviewing Vasily Babbage and his colleagues a week before last, so what I gathered was that some, even before GTD, right, one could argue, and if the underlying ideas were in the air, right, and principle of locality of Fock and some level intuitively understood, right, and one way or other take magnifying glass look and then again find canonical problems. But GTD, I'm quoted, right, as a slogan, right, it helped to, as a philosophy, right, help to crystallize the ideas, to put them on the forefront and raise the importance of canonical problems, which also explicitly or implicitly stimulated various activities in that direction. So as some of my colleagues said, that GTD also helped to popularize this idea to the wider community, right, beyond applied mathematics, including engineers. So able, Joe was very clear and was able to communicate the ideas clearly. So this GTD paper, right, really, John mentioned this as well, right, very concise sentences, very clear to the ideas. So, and in fact, in the end of the day, from Russian school, this kind of it is Keller's not that much philosophy, which is important, but even more so the specific results and ideas, of which there were many, and I was able to mention only few of them today, and there are many more even on that list of influence for Russian school, let alone of the global influence. The conclusion is simple, right? It's again quotation from Vasily Babbage. The influence of Joe Keller's ideas on Soviet-Russian diffraction school was, and indeed remains, very significant. Thank you very much.
I have a comment and a question.
Right.
The comment is about geometric phases.
Yep.
You mentioned the work from the 60s and of course Vladimirsky and Rytov
Right.
earlier. But I learned from Emil Wolf that particular special case of rotational polarization was understood by Bortolotti in the 1920s. But
Right.
the earliest pre-discovery, if you call it that, known to me, a special case, was in 1831 in Humphrey Lloyd's observation of the rotation of polarization by pi in conical refraction, which Hamilton had discovered but not mentioned that aspect of it. So that was my comment. Now, my question is this. A phrase that I've often quoted, which I learned from Kravtsov,
Right.
and which applies very much to a great deal of Joe Keller's work, is attributed to Kinber, sewing the wave flesh on the geometrical bones. My question is, do you have a reference for that quotation?
Mia.
Well, you're the person who would know, coming from this Russian school.
Right. Yeah, maybe I should pick up the details. I will communicate them, and we'll report back, because I don't have immediate answer. Obviously, I'm here the messenger, right? But I will be happy to continue being the one. So yeah, okay. Thank you.
Any final questions?
Can I ask
Tony.
a question? You haven't mentioned Ufimtsev.
Yes, I should have. Yes, Ufimtsev developed a PTD, physical theory of diffraction.
Was he influenced by Keller at all?
I believe so. Yes, I should have, because if Ufimtsev belongs also to Moscow school, explains my rivalry, like for Oxford to Cambridge and other way around, right? I suppose. Yeah, but yeah, to be fair, what we was mentioning, Ufimtsev physical theory of diffraction, it's even abbreviation, right? Analogous, replace G by P, and this is obviously the master.
The results were used by the West, and it was not used by your own countrymen, I believe, quite successfully.
It's edge currents, isn't it? The Ufimtsev theory, basically.
Yes, it's similar like Thanasis will know and some others.
Yes.
Watson's transform versus Kontorovich-Lebedev, for example. You would know, right? Kontorovich-Lebedev is more popular here, and Watson's transform more popular in, but they're quite philosophically closely related, right?
Okay, so on that point, let's...
So this is just an example of mutually beneficial exchange.
We can thank all the speakers in the first session.